27B, number 1. Is the difference between two sample averages just due to chance? To answer this question, statisticians use a blank blank z-test. A two-sample z-test. A two-sample z-test compares the values from two samples. For instance, let's say I wanted to know what is the average height of males at Emory High School. So two of you run out and you talk to as many people as you can. So the first one comes out with 70 inches, and the next one comes out with 71 inches with a particular SD. Then we can compute whether or not those values are the same, or whether they're too far apart to be due to chance. Okay, so we take two samples and we compare them to each other using the difference. We just subtract them and then see if it equals 0 or not. All right, number 2. In 1990 and 2004, NAEP tested the 17-year-olds on mathematics as well as reading. The average score went up from 305 to 307. Do we ring the bells and shout hurrah? No. It's not a very big difference, so we need to do a two-sample z-test to see if there really is a difference or not. You may assume the NAEP took simple random samples of 1,000 in each of the 2 years. The SD for 1990 was 34. The SD for 2004 was 27. In fact, NAEP used a more complicated sample design, but we're just going to make it easy. Can the difference between 305 and 307 be explained as a chance variation? So the 1990 test compared to the 2004 test, we had a sample average of 305, not 205. 305 and a sample average of 307. All right. And both of them were 1,000 students, and that's not really true, but just to make things easier, we're just going to say that. And the SD from 1990 was 34, and the SD for 2004 was 27. Okay, so we need an SE, which is going to be 34 divided by the square root of 1,000. Right? This is average. So because this is sample average, we're going to use the SE for average. 34 divided by the square root of 1,000. And I get 1.075. So I get 305 plus or minus 1.075. Now, just going back another chapter, how would I find a 95% confidence interval? I would double the SE. So 305 plus or minus 2.15. What does this tell us? I am 95% confident that the true average is somewhere in that window. Okay? On the other side, we're going to divide 27 by the square root of 1,000. And I get 307 plus or minus 0.85. So my confidence window, 307 plus or minus 1.7. I am 95% confident that the true average in 2004 landed in that window. I'll never know the truth, but I'm 95% confident that I captured it. Okay? Now, once again, I either captured it or I didn't, but I'll never know. So, what do you think? Are those two numbers close enough to be due to chance? It kind of looks like it. The first one actually captures the second one, and the second one almost captures the first one. Yeah, it's pretty reliable. So let's run the numbers. So excluding confidence intervals, so I'm going to get rid of these. Let's find the difference. Does it matter whether I do 305 minus 307 or 307 minus 305? No. So which way do you want to subtract them? Let's do bigger minus smaller. So I'm going to say 307 minus 305 is equal to 2. Plus or minus what? The square root of 1.075 squared plus 0.85 squared. So square root 1.075 squared plus 0.85 squared. So I get 2, go down, 2 plus or minus 1.37. Now what do I do? Oh, sorry. Should you make a 1-sample z-test or a 2-sample z-test? 2. Why? Because there are we took 2 samples. All right, formulate the null and alternative hypothesis in terms of a box model. Do you need 1 box or 2? So do we need 1 box or 2? 2. It's a 2-sample z-test. Okay, so what is my null? What does the null hypothesis say? So the null hypothesis says that the scores for 1990 are equal to the scores of 2004. So essentially what we're saying is 305 is the same as 307. Or we would say no difference. Those all mean the same thing. Meaning, or sorry, let's do it this way. This might make a little more sense. The difference is equal to 0. Okay? The alternative says that they're not the same and that 307 is bigger than 305, or the difference is greater than 0. Okay? Well, I draw my curve and 0 is in the middle. What is my z-test statistic? What is the difference between 1990 and, well, sorry, 2004 and 1990? 2. So over here at 2. Not yet. That is my difference. It's not my test statistic yet. So I need to know how far away is that in terms of the SE. So I do 2 minus 0 is 2, and I divide that by 1.37. So 2 divided by the answer gives me my z-score is 1.46. Now, we know the answer already. What is it? Accept or reject the null. Accept the null because z is smaller than 1.68. Okay, but the rest of the world doesn't understand that, so I shade norm. So we will shade norm from 1.46 to 5. I didn't clear my draws. Hopefully it doesn't mess it up. And I get a p-value of 7.2%. Now 7.2 is larger than 5%, which means we accept the null, which means we reject the alternative hypothesis. And what's our answer to the people running NAPE? There's no difference between those two scores. And we use the word significant. There is no significant difference between the 2004 scores and the 1990 scores. Okay, the difference is totally explainable by chance. Could the scores have actually gone up? Yeah, we'll just never know. But statistically, we cannot say that they went up. All right. You kind of getting the hang of this? It's basically what we've been doing before. We're just adding in an extra step. All right, number 3. In 1970, 59% of college freshmen thought the capital punishment should be abolished. By 2005, the percentage had dropped to 35%. Is this difference real or can it be explained by chance? You may assume that the percentages are based on 2 independent simple random samples of size 1000. So we have 2 boxes, one from 1970 and one from 2004. The first one claims 59%, and the second one claims 35%. Now, do we really know that those are true? No, those numbers came from a sample. And just to make our lives easier, we're going to say that both samples were equal to 1,000. I don't know what they really were. So I need to compute the difference. Now, once again, the null is going to be the difference is equal to 0. And the alternative hypothesis will be the difference is greater than 0. I need to compute SDs. So the square root of 0.59 times 0.41 gives me an SD of 0.49. And then the square root of 0.35 times 0.65 gives me an SD of 0.48. Those are really close. I'm going to divide that by the square root of 1,000. And I get 1.5, and the other one's going to be 1.49. Or well, 1.5. So we're both going to have SEs of 1.5. Maybe. Wonder what that looked like on the video. SE is 1.5. Okay. So we expect the difference to be 0. Obviously, the difference in our sample is not 0. It's going to be 59 minus 35, which would be 24. So this is 24. Now I need to compute my z-score. Well, I need the SE for the difference, which is going to be the square root of 1.5 squared plus 1.5 squared, which is 2.12. So I take 24 minus 0 is 24, and I divide that by 2.12, and I get a z-test statistic of 11.32, which means we reject the null because it's bigger than 1.86. In fact, it's actually bigger than 2.78? So is there a difference between the 1970 sample and the 2004 sample? Yes, there is a highly significant difference. Do we think that the view college kids have on capital punishment has changed? Yes. There is a highly significant difference between those two percentages. And if you shade norm for this, you would get a p-value of 0. Our calculator won't even pick it up because there basically is no area from 11.32 on this on the standard normal curve to the right of that. All right, number 4. A study reports that freshmen at public universities work 10.2 hours a week for pay on average. The SD is 8.5. At a private university, the average is 8.1 hours with an SD of 6.9. Assume these data are based on 2 independent simple random samples of 1,000. Is the difference between the averages due to chance? So once again, the null is going to be the difference between the two values is equal to 0. The alternative says the difference between the two values is greater than 0. And our numbers are 10.2 with an SD, with an SD of 8.5. And the other one is 8.1 with an SD of 6.9. So I'm going to divide both of these by the square root of 1,000. So 8.5 divided by the square root of 1,000. And I get 8.5%. And then 6.9 divided by square root of 1,000. Oh, wait a minute. I did 10,000. Sorry. Okay, so this is actually, oh, these are averages. So it's 0.21, 0.22. And then 5 divided by the square root of 1,000. And I get 0.27. All right. So I put 0 in the middle. And 10.2 minus 8.1 is 2.1. Now I need to find my SE for difference, which is going to be Pythagorean theorem on those. So the square root of 0.22 squared plus 0.27 squared, and we get 3.5 or 0.35. So 2.1 minus 0 is 2.1 divided by 0.35. 2.1 divided by 0.35 gives me a z-test statistic of 6, which means my p-value is essentially 0. So I reject the null, and I tell these colleges what? What's the end result? Do public school attendees work more than private school attendees? Yes. Yes. Are we sure? No. Is this a significant difference? Yes. Is it a highly significant difference? Yes. Because my p-value is 0. So if my p is less than 5, I say it's significant. If my p-value is less than 1, I say highly significant. And if I shade it normed from 6 to infinity, I'm going to get a p-value of 0, which is highly significant.